Hey everyone, today we'll be factoring quadratics with a leading coefficient that is not 1. Now this is a generalization of the case where the leading coefficient is 1. Like in that case, a lot of the same logic applies. For example, we still want to be turning our quadratic, in this case 4x squared plus 8x plus 4, into a product of monomials. Only this time instead of x plus a times x plus b, we're going to have a few more variables. So it's going to look like k times cx plus a times dx plus b. Now notice that when k, c, and d are all 1, we get the case where the leading coefficient is 1. We get back to this product of monomials. And that's what I mean when I say that this case with a non-1 leading coefficient is really a generalization of the previous case. But anyway, to factor a quadratic like this that isn't a leading coefficient 1 quadratic, first thing you want to do is factor out the biggest constant you can out of every coefficient. Now this step isn't strictly necessary, but it'll usually make your life easier by making the numbers involved smaller. And in some cases it can make your life really easy, because you can get back a quadratic with a leading coefficient of 1. For example, in this case, 4 factors out of all the coefficients. So what we have is 4x squared plus 8x plus 4 equals 4 times x squared plus 4 times 2x plus 4 times 1, which equals 4 parentheses x squared plus 2x plus 1. And this is great. This is a quadratic with a leading coefficient of 1. Which you should already know how to factor. In fact, if you're still shaky on that part, pause the video and try and factor this part of the quadratic by yourself. It shouldn't involve any more new tools that I've yet to introduce, and that's why this is such a nice case. It's convenient because it allows you to use all your old tools to factor this new kind of quadratic. But what if things aren't so nice? What if we have a quadratic like, for example, 5x squared plus 14x plus 8. Here, nothing factors out of both 5, 14, and 8, so there's no way we can reduce this to a quadratic with a leading coefficient of 1, unless you want to deal with fractions, but generally that's not a good idea because it makes the situation much more complicated. What we're going to do in this case is first we're going to see how this product up here multiplies out. So cx plus a times dx plus b. We're going to multiply that out like I like to. Cx plus a times dx plus b. And once again, we're going to find each term by multiplying each column by each row. So here we've got c dx squared. Here we've got a dx. Here we've got bcx. And here we've got ab. Alright, let's collect our terms. We've got c dx of degree 2, c dx squared. We've got a dx of degree 1. And here I'm using different colors to mark different degrees. We've also got bcx of degree 1. And finally, we've got ab of degree 0, or constant. I want this to be equal to 5x squared plus 14x plus 8. What this means is that we need CD equals 5. We need AD plus BC equals 14. And we need AB equals 8. So let's start running through our possibilities. We'll use, again, a table to keep track of things. We're going to need 5 columns. Here we'll put C, D. Here we'll put A and B. And here we will put AD plus BC. Now, first off, we're going to set C equals 1 and D equals 5. Now, this is really the only case for C and D that is different. Because while you can set C equals -1 or D equals -5, or you can switch the two around and have C equals 5 and D equals 1, what you're doing is you're either switching around the two monomials or you're negating both of them. And that ultimately cancels everything out. It gives you the same case. I'll come back to that at the end when we have the monomials, and it'll be a little bit more clear. But for now, just know that 1 and 5, because 1 and 5 are the only factors of 5, barring switching around or negatives, this is the only case that we care about for C and D. Anyway, let's try 1 and 8 for A and B. In this case, AD is 5 and BC is 8. So AD plus BC is 13, which is not 14. So let's try something else. How about we try keeping C and D? Let's try A equals 2 and B equals 4. Okay, in this case, AD is 10 and BC is 4. So we have AD plus BC equals 14. And that's what we want. So we then know that because our original form was 5x squared plus 14x plus 8 equals cx plus a times dx plus b. This then equals 1x plus 2 times 5x plus 4 if we substitute in our values for a, b, c, and d. Now I'm going to touch on what I said previously about the different cases for c and d being the same. If we'd chosen c to be -1 and d to be -5, what we would have gotten is c is -1, so -1x, a is -2, d is -5, so -5x, and b is -4. And you can see that it's not worth checking both of these cases, because there's not really a difference. Eventually, if you pull out -1 from both of them, you get the same thing. And the same applies to switching c and d around, so having d be 1 and c be 5. We would have just gotten c is 5, so 5x, and a is 4. D is 1, so 1x, or just x, plus 2. And once again, this is the exact same as what we did previously, so there's no need to check for this case. If you don't believe me, do it manually yourself, say that it all works out. Okay, let's do a couple more examples. We'll start with 14x squared minus 38x plus 20. Now firstly, because we can in this case, we're going to factor out a constant out of all the coefficients. So 2 factors out of 14, 38, and 20. So we'll pull it out first. We'll have 2 times 7x squared minus 2 times 19x plus 2 times 10, which is equal to 2 times 7x squared minus 19x plus 10. And you can see that now the numbers are smaller already. The new quadratic looks manageable. So we'll factor that with our 5 columns. Here we've got C and D. Here we've got A and B. Here we've got AD plus BC. Now we see in this case that the only factors of 7, up to switching the two around or negating both of them, are 1 and 7. So we might as well just have C and D be 1 and 7. Right, because negating both C and D or switching them around doesn't matter. We also see that AD plus BC should be a negative number, but A and B should multiply to be positive. This means that both A and B should be negative. Otherwise, we can't add them to get a negative number, but we also can't multiply them to get a positive number. So, let's try A equals negative 1 and B equals negative 10. In this case, AD plus BC is equal to negative 17, which is not negative 19. So let's try something different. We'll keep C and D the same. And let's have A be negative 2 and B be negative 5. In this case, AD is minus 14 and BC is minus 5. So we get minus 19, which is great. And this means that 14x squared minus 38x plus 20 equals 2 times cx plus a times dx plus b, which, if we read off the numbers we got, is equal to x, or 1x, plus negative 2, or minus 2, times 7x, plus negative 5, or minus 5. Okay, let's do one last example. We'll do a 45x squared plus 87x minus 42, which, if we try and pull out the biggest constant we can, allows us to pull out 3. So we'll have 3 times 15x squared plus 3 times 29x minus 3 times 14, which is equal to 3 in parentheses 15x squared plus 29x minus 14. All right. Let's factor that smaller quadratic with our table. So 4 columns. We've got C, D, A, B, and AD plus BC. All right. Let's start with C is 1 and D is 15. Looking at the quadratic, we see that 1 of A should be negative and 1 of B should be positive because they should multiply to a negative number. Furthermore, we want the positive number to multiply out to end up bigger. So let's say AD is the positive one. We want that one to be bigger than BC. So with that in mind, we'll have A be a little bit bigger. So we'll start with 14. And B be negative 1. Now this gives us AD plus BC of 15 times 14 minus 1, which is obviously way too big to be 29. So that was a bust. Let's try A is 7 and B is negative 2. The same C and D. Well, this gives us also something way too big. We've got 15 times 7 minus 2. Alright, let's keep downsizing. We'll have 1, 15, and then 2 for A, and negative 7 for B. And this gives us AD is 30, and BC is negative 7. So 30 minus 7 equals 23, which is actually too small. So then there's no point in testing A equals 1 and B equals 14, because that will get us even smaller and it'll shoot us in the wrong direction. So we found out that C as 1 and D as 15 does not work. So we'll use two different values for C and D, because 15 has different factors. 3 and 5 also multiply to 15. So we can use those as our C and D. Once again, we'll start with A being big and B being small. And we see that this time we have AD is 70 and BC is negative 3. So it's not equal to 29. If we try again with A as 7 and B is negative 2, we have AD is 35 and BC is negative 6, and that equals 29, as we want. So our final quadratic will be 45x squared plus 87x minus 42 is equal to 3 times cx plus a times dx plus b, which, if we read off our values, we get 3x plus 7 times 5x plus negative 2, or minus 2. And that's our final answer. And that's factoring quadratics with a leading coefficient of more than 1. Thanks for watching.